Hi, good morning. Can you hear me?
Yeah, we can hear you.
Hear me?
Can you hear us?
Yes, I can. Yeah.
Okay. Yeah. Good way.
So,
So,
yeah, go ahead, Anjali.
Shaopeng. Yeah, so going to do a talk on DevMem TCP. I'm Anjali from Intel and Shaopeng, and there's Dan at the back and Sridhar somewhere here. We've been working on this along with help from the Google team who presented last year for DevMem TCP, Mina and Willem and others. So Shaopeng is going to take away the talk and I'll conclude. Go ahead, Shaopeng.
Okay, thank you, everybody. Yeah. Good morning, everyone. I'm very glad to have the opportunity to share some of the exciting progress on the device memory TCP and also the impact to the AI networks. So let's take a look at the agenda today. That it mostly have two parts. The first one we will recap the device memory mechanism and also our POC. And the second part is mostly for the TCP, how it relevant to the AI networking. And we argued that we can separate the TCP with two parts. One is the protocol, another is the semantic. That the semantic, you can just think it is API, but it is more than API. And we argue that the semantic will play a big role for the future of the AI network. So the device memory TCP is introduced by.
Hi, can you hear me?
Yeah, I can.
You maybe get closer to your mic. We can't hear you that well. You're kind of muffled. Or
Okay.
use a different mic if you don't mind.
Yeah. How is it now? Can you hear better? Yeah. Does this sound better?
Go ahead. We can hear you. That is marginally better. Go ahead. Go.
Okay. Good. Yeah. That device memory TCP is actually introduced by Google last year in the Netdev, also in the Netdev conference. The biggest innovation for this technology is that it using the head split, so it can direct the payload, the network payload to the GPU directly. If you can see my mouse, this is the red line from the NIC to GPU. And in their talk, they also introduced their AI software stack that including the modification for the kernel TCP and also in the NCCL TCP transport. And this page was mostly for a detailed flow that in the user space, you can see that it is the ANC DevMem that was a self-testing tool. And we also use the user tool to reset those NIC drivers. And the third recap is the real-world usage that actually Google already used it in their real product, that A3 instance. And their commercial name for this technology is the GPU Direct TCPX, and the use the Intel IPU for the network need. So the Intel IPU actually has several advanced features for this device memory TCP. That one of them is the address translation engine. That if you are looking at the RDMA engine, there was actually every RDMA engine has a private memory management unit. So for the normal NIC, that we do not have such hardware, but Intel IPU actually has ATE hardware already designed in there.
I've got to pause you for a second. We want to switch to the recording because the audio, if it is not clear, he has sent a recording. We try that. Or this is fine.
Good morning, everyone. I am Shaopeng from Intel. I'm very glad to have this opportunity to share.
Fact, it's the same.
Yeah, do you want me to continue or we plan the, or just the Anjali, you do the talking, that will be much better.
Shaopeng, do you have a headset by any chance?
Yeah, I have the headset, but not me.
Yeah, what?
Sorry about this.
It's just Jamal trying to. Yep. I think. Yeah, keep going. We're on.
The audio is fine on the remote, on the Zoom call, but I think in the room, the Zoom call is probably not being projected well enough.
I see. Okay. Thanks, Mitu. Shaopeng, I guess continue. Not at your end.
Okay. So if in the Zoom the audio is good, so I just reuse this is yeah.
Oh, Shaopeng.
Yeah. I will just restart the sharing. Yeah, we will continue this real world usage and the Intel IPU, the features for this device memory TCP, the ATU hardware engine. And this is the POC, the topology. In the left side, that you can see we have the system A and the system B. That because that currently the TX path is not ready, so in our POC prototype that we only set up the GPU in the system B. So you can see that the all test traffic can come from the system A, from the CPU A, go to the NIC, go to the IPU, and then go to the IPU in the system B. Then the header split was used, so the header will go to the CPU B, and the data will go to the GPU B. And in the left bottom, we have the software design. So we use the open MPI software stack and the OSU micro benchmark. And we also have a user space application that is the RDPM, the receiver side path manager that can manage the GPU memory and also the IPU queues. And we got the pretty good the performance number. almost 3 times that over the normal TCP. The first command is that we use to do the normal TCP to the GPU, and the second command we use it for the device memory TCP, also testing to the GPU. Yeah, this page was a very high-level summary for the status and the source good. Seems a little bit networking, not very good. So that was from Google that we already see that the arcs path. Some of them already upstreamed, and some of them that was still in progress. And they also shared some proposal number, very good one, that comparable with RDMA. And they also have the design, a productive design for the NCCL and the RDPM, but not open sourced yet. Intel said we implement our own prototype RDPM, and also we have modified our driver and integrate into the MPI subsystem. Both are ready for the open source soon. We hope that no later than the end of this year that we can have a product level open source fully completely implementation based on the IDPL. Actually, we have a lot of things to do that we list several of them in this page, but I will not go into the detail. And some of them will be done by Google, and some of them will be done by Intel. And probably some of them will be done by other companies too. Yeah, this is the first part of the agenda. The second part is mostly for the TCP semantic, also the API or the software framework. The TCP protocol itself that actually have some of the challenges that we have a lot of discussion in the already in the Netdev conference that I just copy two of them. But one is about the new protocol HOMA that was try to replace TCP in the data center. Another is about the primary challenge for the TCP. It is very hard to do the offloading. Even after the very good effort for past 20 years, that we still did not get a perfect solution for the TCP offloading. And when we talk about the data center, we primarily have two scenarios. One is the AI, and another is that the other point-to-point communication. That today we will focus on the AI side, the connective communication. And when we talk about the semantic, that we will try to use the MPI as the example. The MPI, the message passing interface, actually that was the version 1 was released in 1994 and is the default communication for the high performance computing. And about the 20 years later, that the AI and the machine learning and comes to as one type of the HPC, and the NCCL was one of the implementation of this connective communication. And why we use this as an example for the semantic? Because if you look into their standard, they have they do not have this MPI is a communication, is a network for the HPC, but that spec does not define a single protocol. Then just define the semantic, then just define the API and the behavior behind this API. So the API and the behavior behind this API, or the meaning of the API, we call it also the spec called the semantic of the network. And we just use this as one of the example. Another example for the network semantic is the RDMA semantic. If you Google RDMA semantic, you probably get already can see some of the discussion about how this RDMA semantic was used, and also the advantage and the disadvantage, etc. RDMA itself is actually was in the first place was defined as a pure protocol for the in-feedback band. So if we can compare these two, the RDMA is the same as the TCP, as the higher level protocol, and the in-feedback band is equal to the Ethernet. And right now that the AI network was using RDMA as the high level protocol, but the TCP, because there are some of the performance issue, we did not use it even for the Ethernet right now. But in this talk, we are trying to argue that the TCP is the same capable semantic for the AI network as the RDMA. But we come back to the RDMA itself, that it also binding to the Ethernet for the RockV1 and RockV2, but and then also have use the TCP as the underlayer protocol. Also, the AWS, the EFA was a kind of also supported the RDMA. But when doing this is largely becoming a semantic, you just meet that the API, you even does not care that the underlayer and the protocol, what is the protocol was implemented in the while. So this is another good example for the network semantic. And also that when it comes to the AI network, that actually RDMA has several very good semantic that we will discuss in the next page, and make it the RDMA was the most popular if we do not send the only one for the AI high performance AI network. So in this page, we will see that we put those semantic for the AI network into three categories. The first one is reliable transport, that we already know that the TCP and RDMA is both meet this requirement, and even that for the scale out network, that the shared memory you can also see as a reliable transport. And the second category was the device direct. So this is what we are talking about, the device memory TCP. For the RDMA side it is called GPU direct RDMA. And the third category is the application direct. For the TCP, we call it zero copy that Mila and Meta guys just shared the zero copy session that was also applied to here. And for the RDMA, it's mostly people call it the memory semantic. Another feature we need is the direct signal from the GPU to network, and this is already implemented in the RDMA world, but we need to do it for the TCP too. So we still have something many things to do, but right now the device memory TCP already have those enhancements for the TCP semantic. We call the TCP semantic. It was defined for the Linux was in the socket API. For the other platform like Windows, then has also have the similar API. For the Linux one that currently that if you looking at the left side the picture, that you can see that mostly the device memory TCP added a new flag for the receive message function, and also added a few message type. And as we discussed, that the TX side direct signal, we will do it in the future. And people may wondering that why it can work slow. That what's the difference? Because that even in the last year, that the OFA virtual workshop, that there was a talk about the RDMA and the Linux TCP. In that session, that in that topic, they also discussed that the TCP API. So there was several drawback. Then argued that it was not enough for the high performance network. And the biggest change was that the innovation usage of the header split. So finally, we can get to GPU memory with high performance. It's actually incredibly good performance according to Google's real-world deployment. And also from the data and the performance data from Google and from our side, that we also can observe that even though that the socket API, the system costs still have a significant overhead, but because the data path is separated from by the header split feature, and we can see that the overall performance was not affected too much, especially for the larger packages. And this is a table that we come up to compare the RDMA and the TCP. So what was the API, that the verbs and the socket API, and also that the infrastructure and the transport that invisible to the user, but that was a big difference. But we have a comparable for the TCP to the RDMA.
Shaopeng, maybe I can take over for a little bit on that slide.
Okay. Yeah, please. Yeah.
Yeah. So I guess, yeah, this is the kind of comparison we saw, or I mean, these are the pillars that we saw in the Falcon talk, in the UEC talk, and then some that Thomas brought up as well. Uri and Nandita and others emphasized, right? So what is it, if we tease out the components, you know, maybe just put the slide back, please. Can you put the slide back?
Yeah.
Shaopeng, just put the slide back, please.
You mean I did not share, or that the page was not correct? Because in my screen that was the 17 page 17.
Okay, good. We are good. Leave it here. Okay. So yeah, so we kind of broke it into the two halves. What is application visible and the rest of the infrastructure stuff. And you would see once we tease out the pieces, they're all kind of learning from each other, and they are getting the benefits on both sides. And I mean, from what we are looking into as a hardware provider is to give you options to choose from, and you know, like being able to give you crypto of the same kind on both sides, congestion control flexibility, and you know, maybe in the future more programmability in the congestion control, like Thomas mentioned, because the innovation will keep on happening in that space. So if we can, you know, look at those comparisons, we would see they're coming very close to each other, except for the transport, you know, the reliable transport. I do see some stuff missing here, but yeah, okay. So reliable transport on a lossy network is what we're looking at here, right? And you know, yeah, I mean, there are networks that on the backbone could be lossless, but in the broader deployment, particularly edge AI and on the front end, you know, we would inherit the network that already exists, which is very suitable for TCP or even Falcon, which has the reliability built in now. Yeah, as you can see, other than one horizontal row, we are actually two, we are matching up. But on the right side, the TCP socket API is the more popular with applications in the RDMA world. So that's what I wanted people to take away from this. I have a few more things to add on. UEC and Falcon, what I felt is like, you know, we have something that is created and we learn from it, and then we kind of just say, okay, it's slight innovation. So we are all open source helps to facilitate building upon innovation. I had a conversation on WESP version 2 with Stefan, which is going to, you know, key off of PSP, I'm guessing. A lot of learnings from there. So yeah, we are trying to bring the AI network performance in comparison, at least for the large packets, closer to each other using DevMem what you would get across the aisle from RDMA. I also want to kind of make a bold statement that Rocky V2 in the standard way with not so good congestion control actually helped pave the path for InfiniBand in the back door, which goes into proprietary space, and I think that was not a great idea. So we want to bring it back to all the cool innovation that has been done in the TCP space by giants like Eric, and use it for the AI networking. Things like Big TCP and lots of other innovations. Some of the things we don't really call out here, but they all help in getting the performance that we see, like RSP or GRO, as you guys know it, and some of the IOMU enhancements that the IPU and DPU vendors have been putting in for address translation, which helps the PCI peer-to-peer completely bypass the platform IMU. So those kind of things, everything adds up to provide that kind of gain. And it's, as Nandita quoted, we have to tease the pieces apart. That's what it is. I think, Shaopeng, you can continue and finish up.
Okay, thank you. The last page is that is kind of the conclusion and the summary that if we look at the current landscape of the AI networking, it's very limited, too limited, with only one RDMA semantic, which was controlled by the single entity, the inferior band, and it also is not designed for the Ethernet. So the TCP is different. TCP is the kind of grow with that Ethernet from the beginning. And if we build the semantic very well, that the software ecosystem very well, that the CSP can just replace the underlayer the protocol if you do not satisfy with the pure TCP protocol. You can change it without the users noticing. So the user still using the TCP semantic for the software, and the CSP can change the TCP protocol. And we list several potential protocols for such replacement. That, for example, the HOMA, they also have this session in this year, and also the AWS EFA, and the most importantly, the focal we just shared in the first day, and also that the Archie said. So we hope that the TCP semantic will play a bigger role for the AI network. Yeah, that's all I have. Yeah, thank you for your attention. That we are open for questions. That back to you, Anjali.
Yeah, thank you, Shaopeng.
If I remember right, you had a comment on one of the slides about approaching RDMA speeds, or any data details on that.
Yeah.
What link speeds? What link speeds were you heading? And it was a single flow, multi-flow?
Yeah, so it was multi-flow, and I think we don't have our final numbers, but based on what Google has observed, it's for large packets, it's very, very close to line rate and close to RDMA performance.
Many flows over 100 gig link or 200?
200 gig, yeah.
200 gig.
In your slide 17, can you explain why the TCP needs an device-side MMU?
Yeah, go back to that slide. Shaopeng, slide 17. Yeah,
17.
So the key thing here, part of you would know, this is device direct. We are doing PCI peer-to-peer. You want the address translation to be encached on the device, either through ATS or device IMU or whatever, so that you're not going to the platform IMU.
Okay, so it's a standard PCI ATS capability.
Yes.
Okay, thanks. So on the slides under transport offload, DevMem TCP, embedded generalized course, that it's hard to imagine how that would ever compare with performance to specialized protocol engines. So I think all the work in TCP, when you get down to it, if the engine is still running in a general core with the general OS, it's hard to imagine how that's going to achieve the performance needed in AI/ML. I suggest you could change one word here instead of generalized, but specialized. And that implies a whole bunch of stuff. We can talk offline, but we still want it to be in cores. You have to run TCP in some sort of programmable core. It needs some generalized aspects, but there are certain things in TCP, if you could specialize those cores, especially how you deal with PCBs and some other things in data movement, you could actually get much closer to the specialized protocol engines, even using fundamentally what CPUs, but they're not commodity CPUs anymore, generalized, make them specialized, then it becomes more compelling.
Thanks, Tom. So I definitely meant generalized and not specialized. TCP is running on ARM cores, and it is, as Shaopeng was pointing out, for the data transfer, these ARM cores are nowhere in the picture. It's only for the protocol handling. And so instead of running on the host, the TCP handling, and I think you can check it out on Google's A3 device memory TCP X, I believe, where they put the TCP stack on the embedded ARM cores. So they are not specialized.
You quickly run into problems. I mean, one thing I've looked at is why is single flow TCP performance so miserable? And one of the reasons is basically everybody's running a single flow on a single CPU, which means that's all you get. You can't get any parallelism. So those are problems we have to solve. Even in a single flow case, it's pretty obvious that you could develop a specialized protocol engine to improve on that greatly.
So, okay, so one thing I want to clarify, we are not competing, because it's not like I'm saying device memory TCP will take the place of RDMA or Falcon or whatever. It has its own place, and you need it, for the backbone networks, for the AI and stuff like that. I'm saying in some places where you don't have the network, in your hands, the ecosystem is a generalized ecosystem, TCP works as good if you discount the latency part, because we didn't bring up anything. There's no comparison for latency here, okay? And small packets. Second thing that I want to mention is, as Shaopeng was pointing out, that payload we are dropping directly onto the memory of the GPU, right? This is something Mina went over in the last talk as well. So the socket API, which is where some of the bottlenecks are absorbed, that are only for the header processing now, and not for the payload at all. So yeah, the protocol handling, on generalized cores for TCP, all the work that has happened will continue to evolve, and it also gives us the flexibility to kind of improve on the congestion control algorithms because they are running on the generalized cores. But just the device direct, which is directly copying, saves a lot.
Oh, right, but if you think about the sockets API, so last NetDev I presented TCP accelerate or TCP offload over AFXDP. Basically, you could have all the advantages of AFXDP, the direct queue access, and get the copy management. So I think my point is, if you want to make TCP even remotely competitive with hardware or the so-called hardware protocols, then we have to do that in the sense that we have to look at how do you apply specialized techniques to this. So I completely agree. People time and time again try to throw out TCP and replace it with something else on the basis that too slow, it's not scalable. I mean, this is going back to the 1990s. Fact is, it's still a pretty popular protocol. And I think the best way to approach it is, maybe at some level you do need these super fancy hardware protocols in order to achieve sub-microsecond latency.
Yep.
But that's not the same thing as saying you can't approach that with TCP if you apply the right techniques. There's still something to be said for trying to improve that. So I like that part of the presentation. But I think if we're going to try to stay on TCP, then let's actually look at the TCP problem.
No, I can't agree more. And, Eric is here. He's going to, do more innovations for us in the TCP space as well. So, long live TCP for sure.
I wanted to respond to that because we know Linux TCP is quite capable of running at high speeds. Problem is how you interface with TCP to get it. And we know the socket semantics have a lot of overhead. So if
Right.
you can remove some of those layers, like I showed in the LPC and Netdev Conf in 2022, you change how you interface with TCP, remove those layers of overhead, and you can get a very fast.
Well, I mean, where do those layers of overhead come from? If you're going through the stack,
we can talk offline, but you can show every place going up and down the stack.
Yeah. So fundamentally,
TCP itself is quite capable at running at very high speed.
It is with some caveats that we have to take offline. So is the congestion control, can you greatly improve upon that if you take it out and put it in the Falcon? Well, TCP, everybody's so ingrained, you have to be in order packet. Break that, and then you're on to something. Now, maybe there's some other thing. So the interface, I would claim, that is not part of the protocol, right? That's above the protocol. So address that. But what I'm interested in is the TCP engine itself. And like I said, the single flow problem is a real problem. It's really difficult because you have I have a paper on this, but you have a critical region. How do you access that across multiple CPUs? Way to get performance is parallelism amongst multiple CPUs. If I'm pinning everything on one CPU, anything you do is going to have bad performance.
We're going to have to cut you off here. Do we allow maybe one quick question?
I don't know if Mina wants to answer about the ordering stuff. You want to say something? Okay.
Mike. All right, I'll repeat what you said. Okay.
Yeah, so I think.
Come to Eric's talk tomorrow.
Yeah.
All right, thank you, guys.
Thank you, everyone. I think we are violently agreeing that we like TCP. That's what I took away from this.
Thank you.